Na Li from Harvard, speaking to us on representation-based control and reinforcement learning for dynamical autonomous systems. Na Li is, as I said, at Harvard. Thank you.
Thank you. Thank you for organizing the wonderful workshop. It's great to come back. I came here, I think, before COVID, 2019. Great memory. So it's great to come back. That time was better in May. The season is, the weather is much better. So today, finally see the true England weather. That's a typical one. But it's better than Boston. So now it's a great pleasure to talk about the work I've been working on in the past few years since I started my sabbatical at Google Brain. And my group at Google is a reinforcement learning group, more from computer science, machine learning background. So my background is more from engineering, control, feedback system. So as you can see from the talk, it has a flavor of both. It's kind of we try to talk about how to restart this topic is how can we bring the success of RL in the computation system to the physical system where things are moving around. And that's the ultimate goal. So I would like to just give a very quick introduction since I think almost everyone here has a great background in reinforcement learning. So when I was talking about the challenges, now move to those physical systems, I do work on all those 4 pictures here that represent 4 different applications, and I had a kind of working on those different applications. First one is the power system, second one is the transportation system, and the robotics, and the last one is a biological system. That's how we also work on the past 4 years. So I will talk about the challenges on these different applications. So many challenges. The talk will cover just a few of it. First about the data. I think everyone talking about data. Like the old RL master is data hungry. But one thing I want to highlight for the data part is when we think of engineers trying to think about innovation of the engineering system, what highlight the innovation part is this. It's not just like getting data difficult. It's when we're trying to improve the system, we want to make the system to behave, not as the system performing now. Let's take the power system example. The power system in the traditional case, normal case, performing okay, well. And we have challenges in the future right now, so we have less and less energy to keep up with the data center. And when there's extreme weather condition, we want to know the better way rather than just doing the rolling blackout. All those conditions means we actually even don't know as a human how to really operate this in a nice way. Not mention how to get the data. And the transportation system, people talk about autonomous driving, people even talk about trying to remove the traffic light, and then still like making everything just smooth, go ahead, cross the corner. Again, we don't have any kind of data experience to know how we're going to do it. And the bio one, even more extreme case, we always want to developing new drugs. We want to grow some new tissues, and we don't have any data for us to really know what's really the way we can even start with. So that's one thing I want to highlight for the data part. It's not just about data quality, it's like we don't have much data for the scenario we want to achieve. And then, like, sometimes, many times, and people, especially for robotics people, would say, we have simulators. How about in the simulators, we try many different actions, which is what RL is doing. We can do the online training. As long as you can find the reward function, you can improve it. So as later you will see, so this is actually one picture. This is actually from my lab. So this is some online. You can easily to find how the robotics fell. So even when we have a simulator, regardless, there's a big gap between the simulator and the real system. And how to bridge the gap is still one of the fundamental problems in the robotics. And safety, all the physical system, one thing, first thing come to being questioned by the engineer application will be the safety. And this is from different applications. You can see the power system, if found something wrong, bad decision, it will lead to cascading failure. Scalability, this is something I also want to highlight. This compared with the success, like say the GPT, the generative AI, once we sending a prompt, we can wait for a few minutes, sometimes once he go with a deep research mode and waiting for the result come back. So, but now for the application, like say transportation, power system, we have those sensors and actuators which deploy at different locations. So we do not have the luxury to wait until a few minutes from the cloud data center to tell us what we're going to do. So we would like to have in the computation and decision making on the spot. And you can imagine you cannot going to put in the big data center, even just put in like one server with 8 GPU in one location. is luxury. It's not going to happen. Now, the last one, this is even deeper discussion. Success of IO in those fancy simulation, and even in the GPT, we're requiring for the reward function. And that's where the IOHF come into play. If you want to improve in the large language model, what's the reward function? For those physical system, again, same thing. The reward function, the outcome is very sensitive to the reward function. When we specify doing engineering design, I also did another sabbatical in another more classical engineering company, Mitsubishi. We tried doing the IO method. It's not going to work well, whether it's about the autonomous driving or it's about, like in the warehouse, how we're going to control some big electrical machine, because the reward is not really aligned with engineering specifications. So when engineering people design the system, you will come with a list of the engineering specification, like this is the response time, this is the steady state error, and how we're going to translate those things into the reward function. Then IO method will just go ahead, optimize the reward function, set for the specification. So this is the one, and another, I know many of here people working on the game theory, and you know that once you're doing the multi-agent, you have self-interest, they come to play with it against each other, it's very hard to know what's the emergent behavior. So those are just some challenges. I'm not saying we have solution for all of them. And while working with those different applications, the one thing I put in the specific application I've been working with is to work with my collaborators, trying to understand the system better, to understand what's exactly the ultimate goal they want to have, listing all the specifications, understand what the measurement they can have, understand what the actuator they can do, and then go ahead using both mathematical algorithm, computational, and also the physical domain knowledge to come with some solution they can go ahead to deploy in different applications. As you can see, like for the domain knowledge, will be different for different application. Today's talk, I will just mostly focusing on the more mathematical and algorithmic side, and to give a flavor of how we trying to find some tools bridging the kind of model-based, model-free, and the domain knowledge together. Now, let me dive into the math. The problem here, I think almost like similar to the morning's talk. So it's actually very standard control question here. We have a state, we have action, we have state dynamics. We're telling from the current state action what's going to be the next state. I'm focusing on the discrete time, the continuous time, so don't need to worry about existence of solutions. So all the system will have a stochastic noise. I put in one variable noise here. And reward function here, I'm focusing on the limit the discounting, infinite discounting reward. So this one, the capital T, can go to infinite. And discounting factor and this feedback policy. The feedback policy, some of you probably from more classical control background, typically when I was doing the control, study that from Caltech, we study the determinist case control. Here, putting the stochastic control, which I will have some discussion for that, like compare with determinist case and the stochastic control, the pros and the cons. But if you, like from control society, this problem is actually very classical, stochastic, nonlinear optimal control problem. Here just some incomplete list of the nonlinear control tools. And you might like, the some of actually textbook, the method will go beyond 89 because I put in the reference here, I put in the textbook as a reference. So I want to highlight, I'm not going to dive into those different methods, is in my memory, I took a one semester class of the SOS tool. I think in the early 2000, people think the SOS tools will bring the hope for solving the nonlinear control problem. It's a computational tool. I took one semester learning it, and I remember the struggling we have. Computationally, it's very, very, very heavy. Like even for the low dimension problem, I remember like for the 3 dimension, the S will be very difficult to get a solution out of it. For different computer, we'll give you different kind of certifications. So this is control, this is actually stabilizable, this is not stabilizable. So that's the difficulty for those tools, and that's why control community, I think when I was a student in 2007, like it's gradually diverging from the SOS, people not talking about that much. And the Kuhlmann control, like it's recently more and more people looking into it. But again, I can have a more discussion after it. I also spending 2 years with thinking about Kuhlmann control probably can be a tool. It also has its own limitations, and because of the representation. So now, I put in this problem that when I studied my sabbatical at Google, I was asking my collaborator is, since they are experts in developing the computation method in RL. So can I just kind of use the RL method as a nonlinear control tools? So first I want to highlight, just even assuming you have the system, all these methods are model-based methods. Even I have everything, the model, the reward, can I just use it as a computation tool to get a control policy? And I will talk about the performance of policy. Questions?
Are you going to require the reward to be bounded, or?
So you will see later. So right now, this just is a problem, and then for the theoretical analysis, it definitely will need something like say it's bounded, but it will come later.
But in this case, the stability is not part of it's not required to define the cost function. If it's stability.
Yeah, I just put it in here, so it's kind of a general one. For the method I'm going to talk about later, even the RAST, when it's not bounded, you can still go ahead to apply. There's a lot of tricks that you play. If it's becoming unbounded, going to a certain threshold, it will stop the simulation, rerun again. So some other thing. Right now, there's no assumptions so far. So that's why I only view this as a computation tool. Like so far, first, it's just as a computation tool to implement it to see what's the performance. But now, so later for the talk, hopefully I will have a time to kind of go finish the both part. The part one, I will just focus on the single system plant. I'm not going to talk about scalability. And second, if I have time, I will talk about how we extend the method for the larger scale system. And for the single plant, I will also first just focus on the model base. As I just want to understand, once I use this RL method, what's going to happen for this system. And then I will dive into, since the method is naturally conform RL, it will naturally extend to the data-driven method. Now, let me dive into the motivation of using the RL as a computation tool for the control problem. Now, I quickly review for the MDP. Just want to highlight the difference compared with the formulation I provided earlier. So in the RL terminologies, it's kind of similarly as almost the same as the model I provide for the nonlinear stochastic control. So the one thing I go ahead to highlight is this one. So in the MDP RL community, people prefer to represent it as the state transition probability rather than the state space model I talked about before. And what this matters, well, later I will talk about in the next slides. And the standard, there's so many different RL methods, no matter what kind of RL method, the way I view all the methods, just kind of put in the two category, actor, critic. For the actor, represent. Now I'm really diving into the computation part. So in order to represent the policy, no matter what, the way people go ahead to do it, you'll find some function approximation. And right now, people always like using the neural net as a function approximation for the policy. So once I have the policy, we'll do, like we have a lot of very nice work talk this morning about the Q learning. So you will do different way like to learn the Q function and use the Q function to evaluate the policy gradient. And the policy evaluation, like you can use in your favorite TD learning, or this morning had a different other Q learning method to do it. And then to go ahead, has an interaction between the two. And another thing I want to highlight, now this is a one function class. For the policy evaluation, so here I'm talking about continuous state, continuous action. So not tabular case. So once we go with those large state, large action space, we also need to figure out what really is the parameterization function approximation for the Q function. And in the toolbox provided by those RL community, well, like I think most of this part right now is going to be feed forward to a layer network fully connected. And if you always ask the question, is really that's the representation that's for me to represent the Q. A lot of experience. So when I started working on it, I tried to use those tools for the problem, control problem I'm familiar with. And unfortunately, I cannot really make the algorithm converge at being stable. So a lot of hyperparameter tuning, there's a lot of those, even the function class, and that's kind of the limitation for the IO computation method if I change my system rather than the matrix simulator. Now that's kind of the first question is, that's what I mean by representation. What should be the right function class that I should start using with? Rather than just making an assumption, hey, this is a function class, powerful, no matter what, you're going to stay with epsilon bound. But that's the question I want to start with, how to choose this representation, the function approximation. So the talk, I will focus on this part, the Q function approximation. Later for the talk, hopefully I will give you 1 minute, 2 minute version of our recent progress on the function approximation for the policy class. Now, let's dive into the critic, the Q function representation. Is this clear for here? I'm just going to understand what should be the representation for the Q function. And this is discrete time. So we already see Bellman equation again and again. So again, this is the Bellman equation under a policy pi, and just with the current reward, and this is the cost to go. Now let's start with this one. Assumption, or say key fact. If my state transition probability can be written down as the inner product of two feature functions. One feature function is on the SA, the current S, current action. S prime is the next S prime. So the inner product I'm just putting here as a general function class, general function space. You can do any other inner product way. So if I have this condition, I substitute this condition into the Bellman equation. This is integration, and the linear product, like this is the inner product, is the linear property. Integration has a linear property, bring back to the Q function. What this says is the Q function, which I was asking, like what should be the function class for the Q, was sitting in this function class. The feature will be determined by the feature from the state transition probability and from the reward function. Again, as I started, I said we start with the problem of the model base. We know the F. We also know the reward function. So it looks like I will have everything, and those from the dynamics and from the reward function will determine what should be my function approximation class. Good for this one. This is the most important slide for my entire talk. I would like to go slowly. This part is kind of straightforward analysis. Now, indeed, so when I started, this is I did my sabbatical 2020. There were a lot of nice papers talking about if my MDP problem, this one, had this structure, and they call this a low-rank structure because compared with the infinite space of SA, S prime, if this one in a product, if the basis is finite, then kind of becoming lower rank. And we'll have a sample efficient and also computation efficient method. When I say computation efficient, because right now when I learn the Q, I don't need to change the parameters of this kind of neural net, like the earlier layers. And all the things I need to optimizing is the last layer, which is the inner product. So kind of you can do this square to estimate W. Yes?
So in the original formulation of the F, so what type of F will guarantee that it's linear structure?
Yeah, great question. So that's actually the question we're asking, like, where does one come from? And now, kind of, we put in that kind of stack, like, why people just making those assumptions for theoretical proofs. Now, let me show you. This is actually one day after a few months, me and my collaborator, we chat, and then suddenly we realized, let me walk through. If I start with the state space dynamics I showed earlier, let's assume in this Gaussian noise, we'll have more discussion about other noise class. But this is actually standard control textbook always start with Gaussian noise. If it's Gaussian noise, I write this state space dynamics as state transition probability. So this is the Gaussian, and then this just put into the Gaussian. So this is now when I say positive kernel, this is the X, this is the Y. So this is always a positive function. For the definite function. So then from the function analysis, and this is using the Bohanna theorem, if I have a positive kernel, it can be decoupled. It's like the positive definite matrix, X, Y. You can split them, X and Y. So that's what's coming. You split, this is the X, this is the Y. And the feature is psi omega, the Fourier series coming from it. And the inner product, this one also will define what the inner product says. For this case, the inner product is the integration according to this, this should be sigma square, sorry for the typo. So it's coming from this random distribution, standard norm distribution. If I put in summarize, what it says is any kind of nonlinear dynamics, I can write this transition probability in terms of two feature inner product. And so far, this one, I haven't really making assumptions of it yet because the only thing it need is this part. Like if I add the Gaussian noise, additive noise, put into that, add the repetition. Yes, please, question.
I don't quite see the dimension. Is this now an infinite dimensional? It's an infinite dimensional.
Again, see, that every time you predict what I'm going to talk about next. So thank you. Right, but mathematically, let's say for that. Mathematically, now we actually find the features that represent the P as the inner product, and this inner product will tell me what's the function class. Now, computationally, since I'm actually aiming for computation method, I need to make this one be finite. So the finite we did in our paper, which already published in Tech, we did a two-feature truncation. One is a random feature truncation because the inner product defined according to the standard norm distribution, so kind of very naturally you can do the kernel tricks. And the other one is kind of similar to the positive definite matrix. You're going to pick the top features, picking those eigenvalues in the function space. So that's the addressing your questions. Any more questions? This is what I can predict the next slide. Is it clear? So in summary, what I want to say is the nonlinear dynamics naturally will give us the feature space. And the feature space, I also want to highlight, like back to here, what really the phi SA is the psi omega FSA. That's why I start with talking about the model-based one. If I have the model, so this method, I'm actually going to use my F. It's kind of like, I like the first talk talking about the model-based and model-free. This is another way to bridge the model-based and the model-free. Because the method I'm going to use is those IO method, the kind of model-free method. But then my function approximation for the Q, I can use my knowledge of the dynamics and to represent my Q function. So with that, this is the algorithm outline. The only thing that changes is to suggest what should be the function class of the Q representation. And this is within the algorithm, parameterize the Q function in this way. And then you can do your favorite Q-learning method, or you can do any kind of your favorite active critique method, and to implement and to see the performance outcome.
If we're interested in learning the dynamic system with additive noise, is there any benefit of parameterizing F directly?
I will dive into the database, data-driven base later. Yeah. Great question. I always predict what I'm going to talk next. So now, so this is the, we start like for the model-based control method. So those method comparison from the model-based control. Iterated LQR, this is the Kuhlmann operator, this energy-based model. The energy-based model is where for the pendulum case, it has the, I want to highlight this one, this paper. So it's one of the senior control professor. First, when he saw my talk, I had pendulum and the drones. He wanted me to find this old paper, which has, he said, in the 1990s, there's a group of people trying to optimize performance for the double bot, the panel bot, and to see whether my controller can achieve the similar performance because it really optimized everything. I'm actually very happy. You can look at the comparison with the double bot. Is we can still do better. And especially one thing I want to highlight is the noise. So the method, the representation, come from using the stochastic of dynamics, and that's where the feature come from. But we can still use this kind of feature coming back for the system without noise. That one I don't have a theory for this part. It still do better. When we have a noise, it kind of naturally follow the theoretical analysis we derive. And you can look at, because all those methods, there are 4 determinist case control problem. So once any kind of perturbation, it's very for the interior LQR, it's going to diverge from the planning that's what did from the offline simulation. And that's why if you look at the performance improvement for the noise case, will do much better. And without noise, it's kind of some other optimized method, it's kind of comparable. Like they're also good because people spend a lot of time optimizing the whole trajectory. So I'm done. I'm not going to talk about too much math for my talk, but if you're interested, so in this paper, we had the theoretical guarantee of the kind of end-to-end guarantee, but with assumptions, like back to the question about whether F is bounded or not bounded. To do it, because we're using the IO method, we actually have to make those assumptions to show overall the policy iteration is improving. So for theoretical guarantee, this is also connection with, that's why I was asking the first question for the first talk. So we also, like, analysis is for this policy parameterization. In the real simulation, you actually can do different kind of parameterization of your pi. So we did this natural policy gradient parameterization, And for the theoretic guarantee, this 3 part of error will come. First is approximation error caused by the feature truncation. And secondly is a statistical error. And because for the Q-learning, this is in the morning, we listen to those Q-learning method. The Q-learning, we train to be the sample-based one, so you're going to have a statistical error. And last one is a policy iteration, because once we do the policy improvement, you're not going to just keep facing infinite number of policy iteration. So the final result is kind of combination of the 3 different errors. And I also want to back to the comment that Sean made this morning. If you check, like for those bound we had, we did on the Labaga measure, L mu, kind of like similar to those kind of L2 measures. And we actually tried initially for the L infinite bound. Initially, we actually made some mistake, and then like we saw we have, it's actually not. Because of truncation, once we did, the transition probability P is never going to be a transition probability anymore when we do the feature truncation. So it's just a function approximation cause all those troubles. Yes.
Yeah, I was just thinking, what is the continuous kind of counterpart of this phi function? So was it like this phi is the gradient of the value function? Because that should be like this little cube, right?
Mm-hmm.
It's Hamiltonian,
Yeah.
and it is dx times.
Yeah, for continuous time,
okay,
just.
So what do you have any interpretation of this phi in the discrete case?
So in the discrete case, the PSA, like the reason.
This phi.
You mean this one, right?
Yeah.
Yeah. So like in the discrete case, as you can see for the representation, come from the side omega FSA, and then showing as a Q representation. The reason why our analysis is on this policy representation, because for the natural policy gradient, so this is a Q, this in total this Q is EXPQ. And for this natural policy gradient, every time when you update, this is also like every time is a EXP. So you can just looking at the theta K, like the summation of all the theta K is the current policy. So the reason we're picking this one.
So
like the meaning is just this one is a Q function, and this is energy-based model is to give us the benefit to do the analysis.
So pi k plus 1 improves over pi k?
Yeah, so this is not the entropy, max entropy RL. So matrix, I have another paper at the end of this one. So this is called the mineral descent method. It's also corresponding to the natural policy gradient. If you parameterize the policy as a softmax policy, you do the mineral descent, then you will have this kind of representation. But if we do the max entropy RL, then you don't have this one. It's going to be pi k plus 1 going to the EXP Q from the previous policy. And these two policy will lead to define kind of diffusion policy we did this year. Again, don't want to confuse audience. Right now, it hasn't really talked about the pi representation yet. The reason we picked this one, this will allow us to do those analysis. And in the interpretation, you see from the previous picture, we actually didn't really do that one. We actually did nonlinear neural net representation for the pi. Good. Now, so the extension, because what we did is just talking about representation for the state dynamics and the Q representation. So we looking into the literature, these people were talking about how to do the safe RL. And like we look at for the safe RL, like where we can put in the representation into the safe RL algorithm. And this is the robustness. And robustness is actually tricky. We did a different variation of it because I can start with the robustness, talking about the feature plus delta. I have two features, phi and mu. So that's what this one we call the duple perturbation robustness. But if my representation, both phi and the mu is not accurate, I think the delta phi and delta mu are what's going to happen. So again, I'm not going to dive into much of this. And this one we didn't really write in the paper, just a showcase. There will be actually a lot of things I think can be done in a more rigorous way in the safety part. But I want to move to the discussion about the data-driven part and back to the discussion about the advantage if you learn F first or you don't learn F. So indeed, my collaborator himself actually want to join. So he has kind of one paper, start with doing the system modification, and then using the learned model to do the feature truncation and getting the policy. But this is the one that kind of just straightforward method to combine things together. But what I want to highlight is since my IO method was really used is this feature representation. It's not really the F. So it kind of motivates, why not just go ahead to start this feature representation directly? Now, when we open it, so even the model-based one, I using the Gaussian distribution, and you can also do some other noise, as long as he has a positive kernel, it's okay, right? It doesn't need to be Gaussian. You want to start with using that as the motivation, like to show how general that representation is. But now once we really dive into this, you can actually view different, like other viewpoint. Like for example, the tensor decomposition, I think in the statistics is like a lot of people actually were working on the tensor decomposition on the high dimension probability distribution. So you can kind of, this is kind of one of those kind of tensor structure being imposed on the probability distribution. So one thing is like based on this equation, right, I can go ahead to talk about spectral density estimation. This kind of based on the equation arrow. If I view this point as the eigenspace viewpoint, I can develop a similar method on the function space, the singular value decomposition. But if I really focus on what we learned, this is a transition probability. So it's a probability distribution, and that's connecting with the discussion we have so far about generative AI. To learn the probability distribution, I can use a statistical tool to do it, rather than to follow this equation arrow, like those kind of standard optimization. So one, we actually did the MLE, maximum likelihood estimator, and this one I think had a huge problem about the normalization, like because of the computation issue. And then we did a contrastive learning, and contrastive learning, again, I think even here I had to put in some, so those references, the reference I found that are very useful for me to learn the generative AI method. It's not, I don't think, not really my papers. Actually, I recommend those one if you want to know the generative AI, how they're using this to learn the probability distribution. I recommend those papers. And the other one is score matching. We had this discussion this morning. And in general, the diffusion models. So it actually has a lot of options. We had, especially my collaborator, has went through all those different kind of way to learn the representation, and each one have a paper. So now we are writing a one overview survey paper to putting all these things together, and we did an intensive numerical study to compare the pros and cons of those methods. So hopefully we finish the paper. We plan to put in the paper online this week, and also all the code, all the toolbox you can go ahead to use. Check my website at the end of this week. Now, so those are kind of general idea. I would say the elephant in the room, which we haven't really addressed well yet, is the exploration and exploitation. How are you going to balance it? So we had for each one of the paper, we had some idea. We using them. We making some assumption to say, oh, this will allow us to do the good exploration. But so this put in the two class. If we do the standard state space learning, right, and then what we can do for this case, we can do Thompson sampling, assume this from function class, and then each time you can just random draw, and hopefully based on the Thompson sampling exploration, like it will allow us to explore well. And the other way, which is for those Q-learning method, we'll also go ahead to talk about the bonus function, right? Since the model we learned is not accurate, so I will add some bonus function. So for each kind of representation, the viewpoint from the previous slides, we develop in the corresponding bonus function to do it. But my honest opinion is even we kind of say we have some theoretical guarantee, but this is kind of buried in some assumptions we made on this, because to really fully touch this kind of exploration, you have to really even have a better understanding of the dynamics we're really working with. But this is overall the general method that people can use. That means you actually can still go back to using the IO method you are familiar with. So this is a numerical benchmark, and when people show this table, will show our method doing better. So I wouldn't spend much time. I want to spend more time on how this representation be useful for the real physical system. And now I'm going to use the robotics as an example to show how the representation will come handy. So I mentioned for the sim to real, it always has this gap. So this simulation has true dynamics, simulated dynamics, true dynamics. They are not sharing the same feature space because my feature representation is based on the state transition probability. So simulator has its own. And if I using that one, I can first use the simulator as a generative model, and I can go ahead to learn the feature. And that's going to be my Q space. But my real P is not going to be the P node. So I have to figure out a new features to add. Now, that's where the kind of linear feature space or the spectral feature come handy. Is think about through the function space. So originally, this is what the function space is spanned. It's on this original feature. And I need to add new features. If we want using the data more efficiently to learn the feature in an efficient way, what are we going to do? First, I think it's kind of some assumption we want to impose, right? Hopefully, the new feature contain as little information as old feature. And then think about what we did for the finite vector space is we can go ahead to impose orthogonal properties on it. I already originally have my old features, and I would like my new features contain at least information as possible. Ideally, if I really know my inner product space, that should be the way I'm going to do. But now we really move to the data-driven side. I still don't know what really the true key is. So the way the approximation, what we did is like now putting this inner product of the two features using the data to evaluate it. Impose as constraint, orthogonal constraint, then to improve data efficiency. Using this idea, so this is how we implement things on the real system. We have a simulator. This is a crazy fly. We learn the feature at the first step. We also will learn some policy from the RL algorithm. And once we implemented it in the real system, as you will see the video, it's not going to work nicely. But once I deploy, I got new data. So once I got new data, the stats seem to real gap. People just go ahead using the new data, improving the policy. What we did is we're going to use the data to also update the feature. At the same time, to update the Q function. Is the clear? So then what we did, let me show you the simulation. So this is from the simulated policy. And the task is actually simple. Just hovering at the target position for 7 seconds. And then this is just go ahead, use the new data to improving, just like run the IO again, but without changing the feature. It's doing better, but again, even within the 7 seconds, it's still cannot really just stabilizing for 7 seconds. And this one is from our policy. It's actually only did 3 rounds of new data gathering. We improve it. That's how it's been doing. When we submit the paper to a robotics conference, and the reviewer found it interesting, asking us, like, then can you actually go ahead and test some robustness? By robustness means you can change the environment. And the good thing for this kind of more like principled feature learning, once I get new data, I can always go ahead and improve my feature space and then improve my policy. So we did, and then now we put in the fact activated. So this is baseline. I hope you see, like, for this one, it had the wind. Initially not doing as well as the without the wind. So we using the new data, we're actually improving our policy by also improving the feature. And then my student, for the next one you will see, we try to change the fan speed. Manually. So if everyone has a very fancy wind tunnel, please let me know. I would like to test this algorithm on a more professional wind tunnel. Good. Now, I only got 1 minute, so we'll just finish like touching this another. If you call like this is, we also went to the imitation learning. This is a unitary robot dog. And for here, let me talk about the advantage for doing this kind of representation learning. So representation learning is like originally when people are doing the imitation learning, they'll just look at the policy, try to making sure the trajectory look like the expert policy. That's it, like without really putting any other domain knowledge or any kind of modeling. So the imitation learning, and that's the challenges it has because expert data is always limited and the computation is challenging. So how the feature representation will help? And this one story also brought another type of feature. So we put in our goal to make our state distribution, state action distribution, like state occupancy measure, look similar to the expert state occupancy measure, which is standard in the imitation learning. So then we writing down what should be the state occupancy measure. And turns out, like this is not the Q. Now I need the D. The D actually was sitting in the mu S prime. The other feature I have already talked about, but the other feature is also useful. The other feature is what tells me what should be the state occupancy measure. And with that, I think I probably can just stop here. And this is what we did for the RoboDog. So I don't have time to go to the scalable control. I just want to tell you, like the feature I was talking about, you can also expand to the large network when you have a multi-agent. And thank you for taking more questions.
We have time for a couple of questions.
Okay, just an engineering question. You'd think that the what's it called? The singular value decomposition extension involving sine waves would be scary to you. Have you looked at like what you get a first order scalar Gaussian linear system, and then you from this method you get a completely wild sinusoidal approximation, right?
So
the
no
functions are sine waves, aren't they?
no, because the representation wise, right, is like even though it's those kind of sine Fourier series, but it's on the probability distribution space.
Oh, it's just on the probability.
Yes, it's on the probability distribution space. It's not like represent F as a sinusoid.
Yeah, but the feed has a sine wave.
Yes, but then it's like the inner product of that. So like the theory
Sure, but
guarantee
your
for
Q
us to
function is a
have.
linear combination of those feeds. And that looks like a Taylor series expansion.
It's not. It's so. I think that's the no. So for this one, it's not.
Okay.
So it's on the probability space. It's actually like still going to be nonlinear, has a v times mu s prime. So it's not. It's different from those Pokemon representation.
Okay.
Yeah.
All right, so we discussed.
Yeah, I can tell. But it's different for that part. And we have indeed to make the method work. Right, for even the random feature truncation, we have a requirement for how many feature we need to have. If the n is very small, then it's not going to work. The inverted Panjang one, we had a 156 feature, and for the drawn one, we had a 2,000 feature. So we definitely there's some like in the paper we had a curve to show like if we start with a small number of feature, and then to go to the like larger space to see how the performance is being improved. So it's definitely sensitive to how many features is needed. If otherwise the gap will be too big, it's not going to ensure anything. Thank you.
I think for the sake of time, let's
Okay, thank you.
thanks for speaking again.